All right, so you guys had a little bit of time to work on factoring these. If you were factoring them like we learned last time, that would totally work. So for example, this first one, I'd be looking for two numbers that multiply to give me A times C, so 1 times 49. But then those same two numbers are going to add up to be my B value, 14. So what are the two numbers that work there? 7. Okay, so 7 and 7. And so if you're going to go through all the steps, that would be how you're splitting up that middle term. So instead of 14x, I would write 7x and 7x. And then I'm just factoring by grouping. I'm grouping together my first two terms. I'm finding a greatest common factor. And so in this case, their greatest common factor is x. And then what's left over if I divide them both by x is this. And so then I'm looking at my next group. So my greatest common factor for these two terms would be positive 7. If I divide them each by positive 7, this is what's left over. And so then when I start to write my factors, I take the GCF from each side. That's one of my factors. And then what's in parentheses should be the same, and that's my other factor. And another way of writing this, since it ends up being the exact same factor, is you could write it like that. All right. Couple of things that we talked about last time. If your leading coefficient is a 1, you can go straight to the factors once you figured out kind of the numbers that work in this scenario. So I could say that this was x plus 7 and x plus 7. But with something like this, if you notice that your first term and your last term are both perfect squares, in all likelihood it's a perfect square trinomial. And so there is kind of a shortcut that works for these. They follow a pattern. So basically, I'm just going to go ahead and show you what the pattern looks like, and we'll use it for the next one. So perfect square trinomials follow a certain pattern, which is if your first term is a perfect square and your last term is a perfect square, and then you notice the middle term is kind of the square root of each of those multiplied together and doubled, then the factor is just going to be a plus b squared. And I'll kind of explain what I mean with that in this one, because it followed that pattern. But as soon as I noticed that I had a perfect square at the beginning, a perfect square at the end, if I take the square roots of each of these, so the square root of x squared would be x. If I take the square root of the b term at the end, the square root of 49 is 7. And then I can check the middle and see if I multiply these together and then multiply by 2, do I get the middle? And I do. In that case, I can go straight to the factor. It's going to be the same. It would be x plus 7 squared. All right, questions for me about that? All right. It is possible to have a perfect square trinomial that has subtraction in the middle, which is essentially what our second one is. And so they'll follow a similar pattern. It's just that the two terms would be subtracted instead. That's all. So if I look in this one, I'm noticing my first term is a perfect square. My last term is a perfect square, so I just want to check and see if it follows this pattern. So I can take the square root of my first term, so the square root of 49x squared would be 7x. I can take the square root of my last term, which would be 1, and then I would just check, does it follow the pattern in the middle? So if I multiply these together and then multiply them by -2, do I get this middle term? So 7x times 1 is 7x, times -2 would be -14x. So since it does follow that pattern, I can just say, in that case, I know that my two factors would be 7x minus 1. And since there'd be two of them, that would be squared. So what are some questions for me about perfect square trinomials or just about factoring in general, since that's something we worked on last class? All right. I'm going to look at the calendar really quick just to point out a couple of things to you guys. So we do have a quiz coming up at the end of this week. And then we'll have a quiz next week as well, and those will be to kind of help us with our next test that's coming up at the end of October. So just keep that in mind. If you want help with anything, feel free to come to Warhawk Time. You're always welcome. And we should have some time to do lots of practice today. So if there's anything you're wanting help with, you can certainly ask me in class. Any questions about the calendar while I have it up? Okay. All right. So we're going to change gears a little bit. We're still going to be doing some factoring today, but we're going to work on the 3.3 notes. So I'll move this, and I'll make sure I scan this and put it on Schoology for you guys. But today we're going to do an extra step. We're going to be factoring, but we're going to solve afterwards. And then we'll also look at how do we find solutions using square roots. So solutions have a lot of different names. They're also called zeros. They're called roots because we can use square roots to solve for them. And if you look at them on a graph, they're x-intercepts. Those words get used interchangeably a lot on things like an SAT. So if you find that one of these words makes the most sense to you, anytime you encounter one of the other ones, maybe just cross it out and put the word that makes sense to you. I'm a very visual person, so anytime I encounter one of these words, I keep thinking x-intercept. And that can remind me, too, that if I graph, I can kind of double-check my answers at the end. All right. But since they are x-intercepts, they are the places where f of x, or the y value, equals 0. Anything on that x-axis has a y value of 0. And so if we're going to solve by factoring, essentially what we would do is we would start by making sure your equation is in standard form. And what that looks like is all your terms are on one side of the equal sign. You'll know that they are because everything on the other side won't be there, so it'll be 0 on the other side. And writing it in standard form means starting with the highest exponent and making the exponents count down. So even if I had an x cubed term, I would do x cubed, x squared, x, and then no x's. All right, from there you would just factor like normal, just like we learned about last class. So I showed you one way, but if you learned other ways of factoring and you prefer those, keep using them. There's a lot of different ways, so it's kind of just a matter of what your brain prefers. Just make sure you're always factoring out a GCF first, if there is one. Oops, used the wrong there. So if all your terms are divisible by a number or a variable, or if your leading coefficient was a negative, you would want to factor out that negative first. And then afterwards, you would just set each factor with a variable equal to 0. So I'll give you a little bit of time to write things down. Feel free to put them into your own words, and then we'll look at a couple of examples in just a moment. Alright, so these are the first two we're going to work on. I'm going to give you a bit of a head start just to see how far you can get with factoring them. But I'm going to walk around in just a moment so I can answer questions, and then we'll come back together. Alright, and feel free to you can use your notes from last time. lots of great work so far. Well done, guys. All right, so from walking around, I'm seeing people put all of the terms on one side, so they're adding 6x to both sides. So it looks like this to get it in standard form. And then I'm seeing to factor this. So what is the common factor for these three terms? It does have one. 3. Yeah. So I would just divide out 3 from everything first. And so the benefit oftentimes of if there is a GCF is it gives you much smaller numbers that are easier to work with. So now I'm looking for two numbers that multiply to a times c, so 1 times negative 15. But then those same two numbers add up to be my b value. Can you guys just shout out what are the two numbers that work there? So it multiplies to negative 15 but adds up to 2. Good, so 5 and negative 3. Exactly. And so from here, you could start to rewrite this trinomial and split up that middle term as 5x and negative 3x. But just to kind of start talking about shortcuts, if my leading coefficient is 1, I can actually go straight to the factors. So I'd have a GCF of 3, and then my two factors. This x squared would have been split up into x and x for my factors. And then one of them would be positive 5, and the other one would be negative 3. But you'll get the same thing even if you rewrite it. I'll show you that in just a second. So in my other class, I did those extra steps where I split up that 2x as 5x and negative 3x. And then I was factoring by grouping. I found the common factor for each two terms, but I still ended up with the same two factors in the end. So questions from me so far? Yeah.
I did negative 5 and 3.
Okay.
That still works.
So the only thing that's going to change is that would, if I change this to negative 5 and positive 3, they do multiply to give me negative 15, but negative 5 plus 3 would give me negative 2 instead of positive 2. Yeah. All right, other questions for me so far? So then the only thing that's really new for today after the factoring is that we do want to figure out where this graph crosses the x-axis. We want to find the solutions. So we're just going to take each factor that has a variable and set it equal to 0. So 3, you can just think of that like an a value. It just kind of stretches or compresses the graph. So these two factors that have x's in them, that's going to tell me where it crosses the x-axis. So I'm just going to put each of them equal to 0 and solve. So if I take away 5 from both sides, one of my x-intercepts is going to be at negative 5. If I add 3 to both sides, my other x-intercept is going to be at 3. So my solutions are negative 5 and 3. And if you're going to write them in like set notation or something like that, just make sure you're always going from small to big. Questions for me so far? All right. Just to kind of connect to the visual aspect of this, because like I said, to me, it helps to think of these as x-intercepts, and that way too, it makes it easy, at least for now while you're learning this, to check your answers. So I do have a Desmos graph that I'll post on Schoology, but I'm going to pull it up really quick just to show you guys that the two solutions we found for this one. So if I zoom out, you can see it is a parabola. It's kind of a wide one. The vertex is really far down. But the two places that it's crossing the x-axis are at negative 5 and 3. So we definitely found the right solutions. Questions from me so far? Okay. So has anybody found the GCF for these terms? Yep. So 3 and what else? And x. Yeah. So if I divide out 3x from each of them, I'm going to have 3x plus 2 left over. And I'm actually done factoring. So when you've gotten to the point that your factors are linear, so what I mean by that is the highest exponent the x's have are 1, then they're not going to be able to break down anymore beyond that. So at this point, I have my factors. They both have x's in them. So I would just set them each equal to 0. And then I would just solve. So if I divide 3 on each side, I'm going to get an x-intercept of 0. So it should be crossing at the origin. And then if I take away 2 from both sides, oops, that meshed together too much. That is a negative. There we go. And then if I divide out 3 from both sides, it'll be at negative 2/3. So same thing again, if you're going to write it kind of in set notation, just make sure you're always going from small to big to show that. All right. And I'll pull up this graph as well, but any questions for me so far? Okay. So just visually so you can see that it's crossing in the right spots. So it's crossing at 0. I'll zoom in a little bit so it's easier to see. So it's crossing at 0, and then also here at negative 2/3, which would be negative 0.6 repeating, basically. Questions for me? Okay. So I'm going to give you 2 more to try, and I'll walk around in case you do want to ask for help. But anything so far from this you want to ask about? Okay. I'm going to scooch it up a little bit, and then I'll write the next 2. So 3 and 4. So 8x squared minus 8x minus 6. And the other one will be 4x squared plus 4x plus 1 equals 0. All right. So take a little bit of time, see how far you can get with factoring these, and then solving for those factors afterwards. All right, but I'll keep walking. Let me know what you want help with. Exactly. We just kind of ignore this. Yeah, you listed at the end one of the factors, but it needs to come into effect here. Yeah.
So in the end, put it in the solution.
It wouldn't be part of the solution. It would be part of the factors. So that the directions for this question were just like factors. That would be the answer. So reading out the GCF, if I multiply that together, it would give you this without the GCF. But for the solutions themselves, only the ones that have x's, right? The x bar crosses the x-axis. Yes, so the only factors that are going into effect for a graph crosses the x-axis, so the x-axis are the ones that have x's. So if I were to plot this, that is kind of like a line, it's like a stretched graph, but then the only ones that are going to affect the x-axis. Oh, you said you're good. So you heard me, you're good. So if it has an accident, yeah, it's going to affect both accidents. Yep. You watch? Alright, seeing lots of excellent work with these. right, these look great so far. I'm just going to show some of the things I've seen so far. So I've seen people notice that there's a GCF here of 2, and so I'd have this afterwards. Even though this is a perfect square, my last term is not, so this is not a perfect square trinomial. So I'd have to factor some of the other ways that we've learned. So once again, you don't have to do it my way, but I'm looking for 2 numbers that when I multiply a and c together, so negative 12, so 2 numbers that multiply to negative 12, but then add up to be negative 4. So can you guys shout out the ones that work? Negative 6 and 2. Fabulous. And so because my leading coefficient is bigger than 1, I am going to have to, if you're going to factor by grouping, rewrite this. So I'm going to split up that middle term. Instead of negative 4x, I'm going to write negative 6x and positive 2x. If you switch the order of these two, that's totally fine. You'll get the same answer as me. But any questions so far? All right, so I'm going to factor by grouping. I'm looking for a GCF for the first half. So I'm noticing those 2 numbers are both divisible by 2. And then for the x's, I can divide out 1x from each of them. So if I divide by 2x here, I'm going to get this. If I divide by 2x here, I'm going to get negative 3. Nothing else divides into these 2 things other than 1, so my GCF there would just be 1. If I divide them each by 1, I'm going to have the same thing. And my check at this point is that what's in the parentheses should be the same. If it's different, usually what that means is maybe you pulled out a common factor, but not like the greatest one, so you just want to go back and double check. But if I list all my factors out, I took a GCF of 2 out of everything at the start. If I take my GCF from each side here, so 2x plus 1, that's one of my factors, and then 2x minus 3 is my other factor. So last class we were just factoring, we were stopping at this point, but today we're solving. So I can see from here I have 2 factors with x's, so I'm going to have 2 x-intercepts, 2 solutions. So I would just put each of those things equal to 0, and then solve like normal. Right. So both of these will be fractions, that's totally okay. I'm going to take away 1 from both sides, and then I'll divide by 2. So one of my x-intercepts is going to be at negative 1/2, and then I would add 3 to both sides and divide by 2. So my other one's going to be at 3/2. And so once again, I'll show you kind of visually on the graph so you can double check and see that you got the right ones. But any questions for me so far? Okay, so I'll pull up the graph really quick just so you can see. So this one is crossing at negative 1/2 and then negative 3/2, or positive 3/2, sorry. So this last one doesn't have a GCF, but I'm noticing the first term and the last term are both perfect squares. So I'd want to check and see if it's a perfect square trinomial, because if it is, there's kind of a shortcut. I can save a lot of time. So if I take the square root of my first term, that's going to be 2x. If I take the square root of my last term, that's going to be 1. So if I multiply these together and double them, I get that middle term. So that tells me this is a perfect square trinomial. And so I can go straight to the factors for that. So 2x plus 1 would be my factors there. But if you factored the other way, you would still get the exact same answers that I did. So any questions from me so far? And since this is the exact same factor twice, when I solve this, I'm going to get the same exact answer twice. So I really just only need to solve it once. So negative 1/2 would be my solution there. And we call this like a double root. And I'll just show you what that looks like on a graph. So it's a double root because it would be the solution to 2 factors, since both factors are the same. And so all that means is on a graph, it's going to be a turning point. So it's going to hit that point and it's going to change direction. So because of what a parabola looks like, that's going to be where the vertex is. So it has only one solution, and that's going to be where the vertex is. So we call that a double root. It'll change directions there. Questions for me about that? Okay. So we've solved by factoring. We're going to solve using square roots, but before I kind of change gears, anything with factoring in general that you want to ask about? Okay. We'll have lots of practice time after this, so if there are things with factoring you want help with, just let me know. But let's go ahead and look at solving using square roots. All right. And actually, I can probably fit this here. Yep. So we're going to go ahead and solve using square roots. And since we are going to be working with square roots, I think it might help just to talk about kind of square roots or radicals in general, just a little quick review about them before we begin. So a review of radicals. So a couple of things, which is you want to simplify radicals. By looking for perfect squares. So well, for square roots, by looking for perfect squares that divide in since we've learned about I, anytime you have a square root of -1, so you're going to replace a square root of -1 with I. And then we always want to be prepared to rationalize. And we looked at a little bit of that when we learned about I, but rationalizing basically just means that we can't have, so we don't want any sort of radical in the denominator. And so you would use multiplication to kind of rationalize. So we're going to look at kind of 4 little mini examples to illustrate some of these things. So we're going to work on simplifying 3 divided by root 6. We're going to work on simplifying the square root of 4 over 5. We're going to simplify the square root of -4. And we're going to work on simplifying the square root of -8 divided by the square root of 7. I'm going to give you a bit of a head start if there are things on here that you feel like you could simplify because you remember how to look for perfect squares that fit into things, or you remember how to rationalize, or you remember how to deal with negative square roots. I'll show these in just a moment, but I'm going to give you a little bit of a head start. So chat with each other, see what you do remember. If you don't write anything down, maybe talk about your thought process. What you're thinking and tracking.
And then you can times these 2 by 2.
Yeah. All right, as you're working on these and getting a little bit of a head start, if you're having trouble with the second one, if I take the square root of a fraction, I could rewrite that as the square root of the numerator divided by the square root of the denominator. Those are equivalent. So maybe that helps a little. So give you a little more time to talk about these. But I've heard lots of great thoughts. I've gotten lots of great questions so far. So that's the right thought. So think of this as uncertainty for a second. In my head, I think of it like this. Yeah. And then that way I can just show that as an I, and then you can see what that is. Okay. Oh, I did 2 or 5. Oh. So it's no serious, it's very specific. What I do is I think of this as the square root of -1 times the square root of 4. And so the square root of -4 represents I. And that is just and well, what is the square root of 4? Yes, sorry, so it's is that exactly 4? Okay, that's right. Okay, so what would we write it like that? What did you say? There's a sheet of numerator. We can do 3 times 4 and then we good. Yep. And then you just want to double check this is what I just multiplied. Oh, the same thing we're doing. Sorry, it's true. All right. So we can go in any order, but do I have some volunteers that could tell me at least some of their thoughts, how they started some of these, what you were thinking about? Okay. So about 1 more minute to chat with your shoulder partners, and then I'm going to call in some people. So be ready. Could be anybody. All right. So, August, can you tell me about one of these that you started to do something with, even if you didn't completely finish? Mm-hmm. Good. So one way to think of this is in your head, or you could even rewrite it, is anytime you have some sort of negative value inside of a root, think of this as the square root of -1 times the square root of 4. And that way I can simplify that square root of -1. That's just going to be an I. And then what is the square root of 4? 2. Since this happens to be a perfect square, it'd be like that. But if it was a different value, so if I had something like the square root of -5, I could think of that as the square root of -1 times the square root of 5. And in that case, I would be able to change this to an I, but since 5 is not a perfect square, it would still be inside of a square root. Yeah, perfect, good. Next person I'd like to hear from is Ashley. Any of these that you did? Okay, so then you're rationalizing. So you're thinking about what can you multiply to that denominator that would turn it into a perfect square. And so the easiest way to make a perfect square is just to multiply something with itself. And then for fractions, whatever you multiply to the denominator, you have to multiply the numerator to keep it equal. So in that case, we would have 3 root 6. Root 6 times root 6 is root 36, which is just 6. And then I would always want to double check afterwards if it reduces down. So notice that I can divide each of these by 3. So that's going to become 1 root 6 over 2. You could even put the coefficient of 1 if that helps you. Questions for me? Yeah. Yes. So I'm going to get rid of the radical for just a second. I'm just going to call it 3x over 6. And so I'd look at this and be like, okay, I can reduce down that fraction. 3 over 6 is the same thing as 1/2. So in the same way that x is like this root 6. So I didn't put the 1 in front just because normally we don't write coefficients of 1, but you could. It's 1 root 6 over 2. Does that answer your question?
Yes.
Good. No problem. All right. So for the second one, I was saying that if you're taking the square root of a fraction, you could rewrite it as taking the square root of each part. And so I'm noticing that that is a perfect square. And if you didn't do the simplifying at the very beginning, that's okay. You can do it at the end. But then same thing, I would want to rationalize this one as well. So the easiest way to rationalize is just multiply a radical with itself. So I'm going to get 2 root 5, and then root 5 times root 5 will just be 5. Since 2 isn't divisible by 5 and it doesn't reduce down, this would be my final answer. But if this were like a 10 or a 15 or something else, I would reduce it down more. Questions for me? All right. So this last one puts a lot of things together. We could rationalize first and simplify afterwards, or we can simplify at the beginning. It doesn't matter, you'll get the same answer in the end. I'm going to go ahead and simplify first, just because especially if I didn't have a calculator, it might help to keep my numbers kind of small. So I'm looking at this numerator, and I'm going to go ahead and see if I can simplify it some. So I'm going to think of it as the square root of -1 to get rid of that negative. And then what's a perfect square that divides into 8? 4. So I'm going to think of that as the square root of 4 times the square root of 2. If I multiply all of this together, I still get -8, but that way I can simplify a little bit more. So for example, I know that that square root of -1 I can represent with an I. I know that the square root of 4 is 2. And since that root 2, that's not a perfect square, it would remain inside the radical sign. So any questions just about getting that far? Okay, so if I rewrite this, my numerator now looks like this. My denominator looks like this, and I would still need to rationalize. So I would still need to multiply root 7 to turn that into a whole number. All right, so before I keep going though, are there questions for me about how I simplified that radical? So I looked for a perfect square that divides into it, the biggest one. All right, so I'm going to keep simplifying. We're rationalizing now. So I can multiply radicals with radicals. So I'll have 2i, then root 2 times root 7 will be root 14. Root 7 times root 7 is root 49, and the square root of 49 is just 7. And then I would see, does 2 over 7 reduce down? And it doesn't. And I would always double check too, now that my radical is bigger, is there a perfect square that divides into 14? But I don't think there is. So this would be my answer. So anything so far with radicals you want to ask about? Yeah? Yes, so I noticed at the beginning here that 4 was a perfect square. The square root of 4 would become a 2. If you didn't simplify at the beginning and sorry, I'm going to show you. So if you didn't simplify at the beginning and you had root 4 times root 5, you'd have root 20. Is that what you had in the numerator? Then you would just work on simplifying this. So you'd be like, oh, is there a perfect square that fits into that? Well, 4 does. And then when I take the square root of 4, I get a 2. So you would still get the same thing in the end. Yeah. Other questions from me? Okay, so we'll be using some of these skills as we're working on radicals, but let's go ahead and look at what quadratics that we're solving are going to look like. So we've done our little review of radicals, so now we're just going to focus on solving by square roots. Right. Which is also sometimes called by isolating, like solving by isolating. And so in terms of steps, we're just going to use inverse operations. So if I think of order of operations as GEMDAS, the inverse of that, if I write it backwards, would be kind of SAD-MEG. To isolate the squared term, so maybe it's just an x squared, maybe it's x and some other value inside some parentheses squared. But this step is similar to things we did in the past, like we would always isolate absolute values before we split them up into their solutions. So same idea here. We're isolating kind of the squared term first. Right. And then once we've isolated the squared term, to undo a square, we would use a square root. We'll just have to be careful because when we are solving, there's a positive and a negative answer that can come from that. And I'll explain that when we get to that step. But I'll try and point that out. I'll try and highlight it so it stands out too. All right. So I'll just fold this so I can keep track. So here's two we're going to try, but it's no different from solving any sort of normal equation. So I'm going to work on isolating my x squared term, whether it's just an x squared or whether it's an x with some other value and that whole quantity is squared. So just think about inverse operations. How would we get rid of that 5 and that 3? How would we get rid of this 3 and this 2? So take a little bit of time, see if you can isolate the squared term. Does anybody think they can tell me some of the things they're doing for this first one? Okay, so I'm going to walk around really quick, and then I'm going to call on a few people to help me at least isolate the squared terms for these. Let me know anything so far you want to help with. Yes, the order of the changes, although we're isolating the x squared, so we're going to define it as 3.
And then you have a bit of egg.
Yeah.
Or mom would teach it.
Yeah.
Wait, did your calcium?
Yeah.
Wait, why?
Oh, does it have to be? Because it was like, I don't know, I just looked at it, the thing, and on the periodic table was smaller. There's any reason that for however being compared to calcium
It's not comparing calcium and everything. It's comparing sodium to potassium.
Okay, well, anyways, whatever it was, I don't know where it was.
But eventually we'll work on things that have an x squared, and so there are things that, just to make sure kind of right on this here, you're talking about like set like that. How do you do the positive negative? Okay.
It's
No, right, so this would be this one.
Oh.
The next name is 2i. No, so if it's not on the 6 square,
the lift years.
that one's negative. Oh, okay, sorry, I was
This side, negative x and positive x. You split it up.
All right, so
To positive x.
can you guys just shout out, how would I isolate the x squared here? So what would I do first? Okay, so I'm going to go ahead and subtract out that 5. So I would always deal with addition and subtraction first for the most part. So I'm going to have negative 12. And then I would deal with division and multiplication next. So I had that coefficient of 3. I need to divide it out from both sides. So I'm going to have this. And now that I've gotten to the point where I have that squared term alone, I'm going to take the square root of each side. And a square root will cancel out. before we write the answer for this, I'm going to go ahead and just illustrate something with a little bit of a simpler value, which is if I just gave you this equation to solve, you would need to figure out every single x value that when we square it gives us 9. And in general, whatever the exponent is going to tell you how many solutions there are. So if I have an exponent of 2, that means there's going to be 2 solutions to this. So if I think about it, 3 squared gives me 9, but then negative 3 squared also gives me 9. So sometimes it helps to see it in like a really simple one, but you're always going to have a positive and a negative answer that work. So what that means is when you get to this step and you're writing the square root of each side, just make sure you're reminding yourself that there's going to be a positive and a negative answer that come from that. Because this has an exponent of 2, it's going to have 2 solutions. So positive and negative. And then how do I simplify something like the square root of negative 4? What's that going to be? So what's the square root of 4? Okay. And then how do I represent the square root of a negative? I. So, what are some questions you have for me so far? Okay. So let's try this again. So once again, as we're isolating, it's no different than when this was like an absolute value sign. Works the same way. So I'm going to work on any addition and subtraction I have first. So I'm going to go ahead and take away that 3. You might be tempted to distribute in this 2. If this squared were here, that would work. But if I think about order of operations, I would need to do an exponent before I multiply. And since I don't want to have to go through all the work of actually squaring this, I'm just going to use inverse operations. I'm going to divide out that 2 from both sides. So I will have this now. Questions for me? So I'm going to go ahead and take the square root of each side to undo that square. And I just want to remind myself that there's a positive and a negative answer that will come from that. Because I have an exponent of 2, that means I should have 2 solutions. So I will have x plus 2 alone on this side of the equal sign. I have positive and negative. And then are there any perfect squares that divide into 5? Can I simplify that more? Okay, so then it'll still just be the square root of 5. And so then I would take away 2 from both sides. So if I subtract 2, it's going to be a negative 2 on this side. And then whatever makes the most sense to you, like this can be my answer, but I could write it as 2 separate ones. One of my answers would be negative 2 plus the square root of 5. My other answer would be negative 2 minus the square root of 5. These are 2 different answers. That's what that plus minus means. I don't want you to like round any sort of answers, but just to illustrate the fact that these are 2 different answers, they're just going to be decimals because 5 is not a perfect square. So if I do negative 2 plus the square root of 5, that would give me 0.24 if I round it. And then if I do negative 2 minus the square root of 5, this one would give me negative 4.23. All right. And just to illustrate again that what we're finding are x-intercepts, I'm just going to pull up the graph for this really quick. But any questions for me so far? All right, so if we look at the graph for this one, it is crossing at so that was when we subtracted, we got negative 4.23 or 24, and we got positive 0.23 or 24. Questions for me? Okay, we're going to do one last one, and then we're done for today. The last one I want you to see how far you can get on your own, but I also want to use it to talk about common mistakes. All right, so when we were testing on absolute value, so if instead of a squared here, if this was an absolute value, a common mistake I saw here is people were combining these together to get 7. So rather than combining them together, think of them as 2 different operations. This is adding 2, and then this is 5 times this, so you would undo that using division. So combining these together is not going to work. So just be careful with that. If you're isolating, use inverse operations to do that. All right, I'm going to walk around. Anything you want help with so far, let me know. This will be our last one before we close out this lesson. Practice. All right, so we'll just go ahead and check this really quick. I know a lot of people have finished, and there are a lot of things about these that look great. But you would take away 2 from both sides first. And then you would divide out that 5. And at this point, we're taking the square root of both sides. So I just want to remind myself there's going to be a positive and a negative answer to that. So I'll have 2x minus 1 equals positive and negative. And it might help to start simplifying the radical now. So my goal is I want to look for any perfect squares that divide into negative 12. And I also want to think of that negative as like the square root of negative 1. So what is the biggest perfect square that divides into 12? Yeah, so I think of this as times the square root of 4 times the square root of 3. And that way when I simplify, I can say the square root of 4 is 2. The square root of negative 1 I'm going to represent with an I, and then that 3 is not a perfect square. It'll still be inside of that square root sign. So I'm just going to replace all of that with what I just got, 2I root 3. Question so far? Okay. So now I'm going to add 1 to both sides. So it would be a positive 1 on this side. And then I'll divide out that 2 from both sides. If both of these terms were divisible by 2, so if this was like a 2, 4, 6, some sort of even number, then I would go ahead and divide each of them by 2 and simplify further. So any questions from me about this? Yeah.
If they were all divisible by 2 and the I number in front of the I was like 6, would you do 6 divided by 2?
Yeah, so like if instead, if this were something like 10 plus or minus 6I root 3 all divided by 2, then I would simplify that and say, all right, that 10 divided by 2 is going to be 5, 6I divided by 2 is going to be 3I. I would actually divide them, yeah. Other questions for me? All right, so we are done. We're just going to practice. There's a delta math, and then I also have a paper practice up here.